We're very glad to have with us Paul, who is a very bright final year PhD student. He's come here to talk to us about adapter signatures. So let's give it up for Paul.
Thank you. I don't have a time limit, so if you just want to leave, it's fine. But I was really happy to make these slides, and I covered, I think, too many topics, but we will find out how it will work. So for next, I guess, 45 minutes, I will talk about a problem which is really easy to describe, but kind of hard to solve. The problem is the following. Imagine you have two parties, Alice and Bob. Alice knows an NP statement, big Y, and she's really curious about the witness for the statement. And then there's Bob. Bob knows a witness, which is good, and he actually wants to sell this witness to Alice. This problem seems not too tough, but we have the following problem. Neither Bob trusts in Alice, nor does Alice trust in Bob. So whoever party needs to send the witness or the payment first kind of loses. Let's go back to this situation. Imagine Alice sends the payment first because she's like, okay, let's pay Bob, and then eventually we'll learn the witness. However, after Bob learns the witness, he will just, after Bob gets paid, Bob will just go offline. Same holds for Bob, right? So Bob says, okay, let's send this witness first, but eventually Alice won't pay. So we are kind of in a deadlock situation in here. And adapter signatures are the perfect primitive if you are ever in this situation. What you will learn today are three things. First of all is today, like really today, with the current version of Bitcoin, you can solve the fair exchange problem of a coin for a witness using adapter signatures. Then you will learn what are adapter signatures, why are they useful, and why should you be careful when you use them. I say be careful because there are many literature out there for adapter signatures. And as you will learn today, maybe the formalizations you will learn there are not the ones you actually see. Okay, let's start with adapter signatures. Adapter signatures continue of two things, right? Adapter and signature. So when we build them, it's again built from two things. The first one is a signature scheme. I think most of you know signature schemes. It's kind of, you have a key generation, a signing, and a verification interface. Like standard, like signing takes a message and a key, gives you a signature. Verification takes a public key, a message, and a signature, and gives you a bit. In addition, because we want to exchange a payment for a witness, we need a hard relation. And a hard relation is simply contains a single algorithm which generates a random instance of this relation, and it gives you a statement in a witness pair. Okay, so this is pretty standard. So what do adapter signatures do? The first algorithm we get is the pre-sign algorithm. It takes as input again the signing key message, but in addition, compared to signing, a statement, and gives you something which we call a pre-signature. If you have never heard about adapter signatures, imagine this pre-signature is kind of a verifiable encryption of a signature on M under the statement. The next algorithm is the pre-verification algorithm. It takes a message, a pre-signature, and a statement, and a public key. And you kind of can see this as the verification that this encryption here or this pre-signature is actually well-formed. So when you get a pre-signature, you can publicly check if this pre-signature is well-formed or no. Then you have an adapt algorithm, which kind of also takes the public key, the pre-signature, and the witness, and gives you a signature. This can be viewed as the decryption in our little mind experiment. And then there's the extract algorithm. The extract algorithm reads a pre-signature and a signature, and eventually leaks a witness. Okay, now we have these algorithms. How do they solve the fair exchange problem? Remember, we have Alice and Bob. Alice who wants to learn the witness and Bob who wants to learn a signature. I said he wants to be paid, but if we are in the setting of a blockchain, we will see in a second that if you learn a signature, it's might as well as good as being paid. Okay, let's start. So Bob generates a statement witness pair, sends a statement and the message to Alice. In this case here, the message corresponds to some transaction for the blockchain. Then Alice computes the pre-signature on the message and the statement and sends the pre-signature back to Bob. Now Bob, he knows the witness, he knows the pre-signature, so he can run the adapt algorithm and post the signature on chain. Now, I said before, nobody wants to send first. Why is Bob okay with sending the signature first? Well, this is the case because Bob simply sends a signature whenever the signature is sent, and post it on the blockchain, Bob received a valid payment. So from this point on, Bob can go offline. We can just consider Bob is not there anymore. However, whenever the signature is posted on the chain, Alice can observe the signature from the chain. And having both the pre-signature and the signature, Alice locally can run the extract algorithm and hence learn the witness Y. So we see in this situation, no party really sent first because the only message that reveals information is the signature. However, when the signature is posted, Bob is immediately paid, so he kind of didn't send first. In addition, when the signature is posted and Bob is paid, Alice at the same time can extract the witness. That was like my first bullet point. Why are adapter signatures useful and why do they solve our problem? Yeah, and then once I explained this, most of the time people ask me, okay, that sounds nice. Maybe it's kind of tough to build, no? Like it seems a bit like witness encryption, maybe. And the good answer is actually adapter signatures are really easy to build. Imagine this Schnorr signature scheme in here. No worries, it looks a bit complicated, but I will guide you through. So for Schnorr signing, you will sample a random element, compute a commitment to this element. And when it's not a pre-signature, simply hash the transcript used for fiat Shamir, and you return R and secret key times C plus R. To update this into an adapter signature, the only thing you have to do is multiply the Y element with the R. Why this makes sense, you will see in a second. Okay, pre-verification is pretty much like verification for Schnorr. You simply verify the public equation. Okay, we added Y to the R, so we also have to add Y here. But you see, this is not a valid Schnorr signature yet. Without multiplying this Y, like how we would do a Schnorr verification, it won't be a valid signature. Okay, but we can turn that the pre-signature into valid Schnorr signature by simply adding this Y to the second element in here. As you see here, now we have R times Y as an updated commitment and R plus Y as an updated randomness. Therefore, this adapted pre-signature will satisfy the standard Schnorr verification equation. Once we have this, extracting is pretty simple because we simply learn the second element of each signature and pre-signature, we subtract them, and because adapting was adding Y, extracting will now lead into Y. And that's actually really important. Like we want adapting and extracting to be efficient. And at the same time, we want adapting and extracting to be efficient. At the same time, we want the verification equation to be unchanged to the standard Schnorr verification equation. That's the case because we want to post the signature to the blockchain eventually. Yeah, and the problem I told you was like exchanging a coin for witness sounds a bit abstract, right? Like, why should we do it? And this problem was introduced and solved with adapter signatures in 2017 by Andrew Polestra, and Lukas Aumeier and a bunch of other people formalized adapter signatures in 2021. And then once they were formalized, people saw, okay, great, if we solve this fairness problem, we can actually bootstrap this and solve all kinds of problems. One of them is payment channels for which adapter signatures were designed. However, we can also do coin mixing, Oracle-based payments, and a lot of other stuff, actually. After we got a bunch of applications, people also considered theory and built post-quantum adapter signatures or stronger definitions. Okay, let's see how we can bootstrap adapter signatures to build a good protocol. Imagine you want to make a payment channel. Payment channel kind of says you have two parties, Alice and Bob. Alice and Bob want to exchange a bunch of payments, but they don't want to post on the blockchain every time. So what they are doing is Alice and Bob are locking coins on the blockchain once, and then they updating their state locally. And once they have updated their state, they can finally close the channel and make one post to the blockchain again. If you look at this, if you look at the blockchain, you see two payments. But if you look in the state between Alice and Bob, you can see that they maybe have updated the state a bunch of times without doing any posts. Okay, how to open a payment channel is relatively straightforward. Alice and Bob simply lock coins to the channel. Locking coins to the channel kind of means the coins are not controlled by Alice or Bob anymore, but only by Alice and Bob. So both parties have to agree what happens to the coins in order to spend them. Once the coins are locked, updating the channel also is kind of fun. So what parties are doing is, first of all, they are exchanging a whole bunch of statements, XA, YA, XB, and YB. Second, they pre-sign the new state, sending a pre-signature. And as you can see here, Alice will pre-sign the statement of Bob, and Bob will pre-sign the statement of Alice. And once they have exchanged pre-signatures, which kind of updates the channel state, they also exchange witnesses YXA prime and XB prime. Why do they exchange these X values? Well, these X values are coming from a previous session where they exchanged XA and XB. And once these witnesses are exchanged, this means, okay, I don't want to have the old channel state anymore because I now have an updated channel state, which was signed by Alice and Bob. Okay, now to close the channel, there are two ways. There's the honest way in which Alice and Bob just decide, okay, I like my final channel state, let's sign it. So Alice signs, Bob signs, and they just exchange signatures. Once they have exchanged the signatures, they can be posted on the blockchain, and the updated channel state, in our case here, 4 coins and 4 coins would be posted. However, what can also happen is that one party misbehaves. Imagine here, like Alice would very much prefer the previous channel state where she had 5 coins instead of having only 4 coins. So we need a second way to close a channel, which is a forceful closing when you post a signature of B, like of Bob, and the witnesses of Alice, or the witnesses of Bob and the signature of Alice. Why we need the second branch here, we will see in a second. Okay, so imagine we have two, like remember how to close a channel, either both signatures or witnesses and a signature of another party. So imagine A wants to try to close on an old channel state. Remember here, like she had 5 coins before, now she has only 4 coins, and she's like, okay, let's close back there. To close in here, she needs to provide a signature of Alice and Bob. So what she simply can do is she signs on her own. Then she adapts an old pre-signature of Bob, which is a way to obtain a signature. And then she can post, sorry, this first one is wrong. She simply posts sigma of Alice and sigma of Bob. So she posts 2 signatures, not this here. And then she has to wait for tea time and would be good. However, in this tea time, Bob can come in and say, okay, hey, wait, Alice, you closed on an old channel state. I can prove this channel state is old because I know XB prime, which is my own witness. And I can extract from you the YA prime because you adapted. And I know signature. So Bob can close the channel before Alice rewinds because Alice needs to wait for tea time. Okay, well, that's fine, right? Like if Alice wants to close on an old channel state, Bob can use the extract property of adapter signatures and the fact that Alice exchanged the old channel state to close before Alice can claim the coins. Second case is, what happens if A is just inactive? So Alice just lost 1 coin and she's like, okay, I cannot go back to the old channel state, but if I'm just inactive, I can still punish Bob because I just don't do anything. So what now happens is, Bob goes to the latest channel state. He adapts the pre-signature of Alice, which he knows because Bob knows the YB, and then he waits for tea time. Why can't Alice punish this? Well, they never agreed to close to mark this channel state here as old because they didn't exchange XA and XB. They only exchanged XA and XB for the previous time. Therefore, Alice cannot do anything but just wait for the channel to be closed on the latest state. And here we can see pretty good why adapter signatures are useful. If you want to close a channel state, you can only do so when you reveal a witness. And then we can use this witness for these payment channels, for example, in here, and say, okay, if you provide a witness to me, and then I can, like if you want to forcefully close the channel, you provide a witness. If this witness corresponds to an old channel state, I can punish you. Does this make sense? Do you have any questions? Like if this is fine for you, I would go on.
Makes sense.
Okay, cool. Okay, so the first work I want to talk about today is Foundations of Adapter Signatures. It appeared at Eurocrypt 24. And what we tried to do is we were looking at all kind of adapter signature protocols. And we found out that the formalization for which adapter signatures were built, it's kind of the formalization for payment channels, which I just showed you. However, other protocols which were used other protocols which were built based on adapter signatures use a kind of a different setting. So formalization seems not too much. And then what we found out is that actually, like most protocols using adapter signatures have kind of a flaw in the proof because of this fact. And we updated the definition to get new definitions to fix these problems. Okay, as I just said, adapter signatures were formalized to building payment channels. And the goal was of other people that use adapter signatures that the formalization for payment channels in here is really similar to the formalization of coin mixing and basically all other applications. And what we found out, there's actually a gap between them. Okay, let's look into it. As I said, we have Alice and Bob. We have the situation here. Bob is sending a statement and a message. Alice is pre-signing, and then they're exchanging the signature. That's what we just described, and we saw in payment channels, that's kind of what's going on. However, the problem is this definition is a one-shot experiment, which means the adversary can only learn a single challenge per pre-signature, nothing more. Second, adapter signatures only achieve existential unforgeability, even if the signature scheme is strongly unforgeable and the relation is one-to-one. There are situations in proofs where people used one more assumptions where this is a real problem. And third is the signer, which is kind of Alice, cannot influence the statement because Bob sends the statement. We found applications where Alice is actually also computing the statement, and then all kind of stuff can go wrong. Okay, let's look into the definitions. I said adapter signatures were formalized for this setting. And if you look in the most used definition for adapter signatures, it's actually built like this. Okay, so you have the security experiment, what's going on? You have a key generation. You have an adversary having access to pre-sign and a sign oracle, and he will eventually output a message M star. Sign oracle simply signs, pre-sign oracle simply pre-signs and stores the message for which is signed or pre-signed in a set. Then after this happens, there's a challenge phase in which we generate a statement witness pair, gives the statement to the adversary, and pre-sign on the adversary chosen message. And the adversary kind of outputs a signature afterwards. And similar to the unforgeability of signature schemes, the adversary wins if the message M was never signed or pre-signed in our oracle, and the verification succeeds. However, if we look at the protocol in detail, we see that the adversary learns a pre-signature on M star, but only one. Like for M star, he cannot use any other oracles. And that's going to be a problem. So what we did is we found a adapter signature scheme that used this fact that you only learn a single pre-signature on the challenge message to break stuff. So what's going on in our signature scheme in here is, what we're doing is we're simply pre-signing on a message, and additionally we are signing. What we then are doing is we're deriving a randomness using a random oracle and blind the signature. In the end, we output the pre-signature and RB. RB is either the blinding value or the signature. Okay, why is this a problem? I mean, that's really contrived, right? So what you can see is when you learn a single pre-signature on M, you don't learn any additional information to before because RB is either like a perfectly blinded value or a blinding value. But since you learn only a single pre-signature on a message, that's no additional information you actually learn. However, when you learn the second pre-signature on M, you will learn a valid signature with probability 1/2. As I said, this is not a problem for payment channels, but we showed that if you use adapter signatures to create oracle-based payments, for example, this will break your security proof. And this was the conclusion of our first work, is that we have extractability and adaptability, which are security notions for adapter signatures. And the versions you will find online in most papers are not the versions we have. And if you use these versions, so these counterexamples I just showed will arise most certainly. So when you use adapter signatures, choose your definitions wisely. The two definitions we have is extractability, which says is whenever there's a signature on a message M, then either the signer already signed the message or the signer knows a pre-signature that allows extracting valid witness. So kind of signatures are unforgeable. However, if you learn a pre-signature, then I can extract. This kind of protects the signer. The second security property is adaptability, which says if you learn a valid pre-signature and you know a valid witness, then you as well will learn a valid signature. This protects the Bob in our case, because Bob is sure once he posts a signature on the blockchain, he will be paid. In addition, we found two other security properties. They are important to fix special applications. But for most applications, most likely extractability and adaptability will be sufficient.
Paul, can you give an example of a special application?
Yeah, for example, in the coin mixing case, which I have some extra slides on, you have a proof based on a one more assumption, which means we can just go there. No, we can't. So we have just a one more assumption, which means every pre-signature should just reveal one single witness. Because then you have like how many challenges you learned, how many help oracles you used, and then the proof works. So for coin mixing, for example, you need extractability that you don't learn two witnesses. But if you are going for a payment channel, for example, if you learn a second witness Y prime, nobody cares because you need to provide one single witness for this statement, but not two or three. And pre-verified soundness is in whenever you have like the situation that not Bob is sending the statement, but Alice is creating the statement, you need to be sure that the statement is well formed. That's kind of a pre-verified soundness says.
And that is also used for mixing, or is it something else?
This is used for Oracle-based payments. Let me go to my bonus slides. Here. Okay, let's see what happens in, for example, in Oracle-based payments. In Oracle-based payments, it's pretty much like you have Alice, Bob, and the oracles, and Alice is sending a payment when the oracles are testifying. Okay, so how the protocol is built is, at first, Alice creates a bunch of statement witness pairs, sends the witnesses to the oracles, and the oracles, and then Alice pre-signs a whole bunch of messages on the different statements and sends the pre-signatures to Bob. Now, when the oracle wants to testify for an event, it simply sends YI to Bob, and Bob can use the pre-signature it knows and YI to be paid. That makes sense, right?
Mm-hmm.
But now you see in here, the statement and the pre-signature was computed by Alice. And the adapter signature security notions only give you adaptability if the statement is well formed. So if Alice now creates a statement which is not well formed, you don't have the adaptability guarantee.
Okay, thank you.
And here you can also see why having multiple pre-signatures on the same message is important, because here, in general, like Alice could also sign the same message twice or three times, and then Bob would learn the full adapted signature with our leaky counterexample without waiting for the oracles. Okay, let's go back. So yeah, so when you use adapter signatures, a good starting point is just to look at the Eurocrypt paper and look for the definitions. If you read any other paper with different definitions, I mean, they can be right, but you should be careful if the definition fits the application. Okay, once we had good definitions for adapter signatures, we tried to compose adapter signatures with different primitives, which is the second paper, which is called UC-secure adapter signatures. Why do we want to compose adapter signatures? Well, the thing is, adapter signatures are mainly used in higher level protocols where you have an adapter signature, maybe some kind of encryption or some NISIC and other stuff going on. So you don't want to look for adapter signatures as a single primitive, but you want to see how it interacts with other protocols. And this idea was not new to us, but it was also already used by Tyree, Monero, Sanchez, and Schneiderwind. And they provide a UC definition for adapter signatures. If you have a UC definition, building bigger protocols is way easier and way better. But we found out that this definition they propose cannot be realized. And then we started investigating it and provided a new functionality. So first of all, maybe not everyone is, yeah?
Cannot be realized, so they just gave the definition and no construction.
Yeah, we show that no adapter signatures can realize this functionality. And at the same time, even if you could realize it, you don't get the security guarantees you would expect.
Okay.
It turned out to be extremely tough to make this functionality working. It took us more than 6 weeks, like just to look at the single functionality, and we continued to find bugs and more bugs and then try to fix them. And it's like a really hard problem apparently, but it seems easy because you see secure definitions for signatures and you're like, okay, let's add like 2 algorithms and it should be good. But it turned out that adding these 2 algorithms, it's a hard problem. Okay, for UC functionalities, how do they work? It's relatively straightforward in a high level, and it's really hard in the details. So on the high level, you say you have an environment, which is called E, and the environment either has access to a protocol, and a protocol means like, for example, adapter signature for exchange or something, or the environment has access to an ideal functionality, which is secure by design, and it can seize interactions of a simulator with the ideal functionality. The idea is that the environment cannot tell apart if he sees the interaction of a real protocol or the simulation of an ideal protocol. And now the cool feature is that if one building block is secure in the UC setting, then you can simply replace this building block in the real protocol by the ideal version. Which means that, for example, for signatures, you don't have to care about unforgeability because the functionality for signatures has unforgeability built in. And now comes the functionality, no worries. You don't have to read this. It was meant like it's just for completeness sake. I have a simplified version of this functionality in here. So the functionality it makes sense. So when you look at it, it should be like this. Unfortunately, it's not, but like it should be. So what's going on is whenever you're signing, you ask the adversary, okay, give me a signature. Then if the signature is marked as invalid, like the adversary provided something which we already said, no, that's not valid, then we return 0. If the signature is not invalid, we add it to our set of what messages we signed, and we return the signature. And now if we verify, it's also kind of straightforward. We just look in our set queue, did we sign the signature before? And did we verify the signature before? And we already decided on if the signature is valid or no. If so, we return the same value. This is kind of consistency or correctness, right? Like if we signed and we returned it, or if we verified before, we will always answer consistent. Second thing is unforgeability. If this message was never signed before, it cannot be a valid signature, then it must be forged and we will return 0. And then if it's not the first case and not the second case, which kind of means we have already signed this message, but we don't know the signature yet, then we let the adversary decide if it's a valid or an invalid signature and store the signature to our set. This makes sense, right? Like you have signed in an oracle, and whenever you see a signature, you answer consistent, you enforce that there's no unforgeability. Yeah. Then when you want to adapt, so the left side here is kind of standard and also used for signatures. That's why I said it should not be too hard to extend this functionality to adapter signatures. Now, if you look at the adapt oracle, what's going on in here is if you have never seen the pre-signature before, simply return an error. And otherwise, run adapt locally and store the tuple pre-signature, signature, and witness in the set queue. Now, if you want to extract, you can simply look if the tuple is in the queue. If it's in the queue, you can return it. Otherwise, you return bot. And at the first look, this functionality makes total sense. Like you have the signature functionality on the left, and on top you have like these 2 oracles, which kind of are similar in flavor to the right ones. However, there are a bunch of problems. Like the first problem is that this functionality requires pre-signature unforgeability. What do I mean by pre-signature unforgeability? Well, you see in here, if the message was pre-signed, like it was decided on the pre-signature before, we return consistent values. However, if the message was never pre-signed before, we return 0. So no pre-signature can be valid when it was not pre-signed before. That's important. And now look how we build a distinguisher. So we have the following adversary. What he does, he calls a sign oracle. He gets a signature. He samples a statement witness pair. And then he backwards adapts the signature. This works, for example, for Schnorr signatures or for basically every adapter signature there is. at the moment. And if you now call the pre-verification oracle, it can see that this message was never pre-signed. So the pre-verification oracle will output 0. But if it outputs 0, there's a bug because this should be a valid pre-signature. And when I mean there's a bug, I mean that the environment can distinguish between a simulation with the ideal functionality and a real protocol. And as a matter of fact, this leads to the conclusion that Schnorr adapter signatures, which are the most used adapter signatures, cannot realize functionality. So no matter what you do, there exists no simulator that can simulate this behavior. A second problem we found is that extractability, like one of the important security notions for adapter signatures, is actually not formalized. We look again to the oracle for extractability and we see, okay, if this set was previously stored by adapting, then we return it. Otherwise, we don't return it. And that's inherent to do so because in the way that functionality is designed, the signatures and pre-signatures can be anything. I mean, if the adversary creates them using a forgery or something, we cannot simply run the extract algorithm because there's no fixed algorithm here defined because the adversary simply provides these values. Okay, so the problem is any valid signature, extractability says any valid signature either extracts with a pre-signature known by the signer or it was previously signed. Now, as we look at the adversary, he can do the following. He creates a relation, runs pre-sign, samples a random pre-signature, runs OP verify, and if you remember, the adversary can decide if it's valid or no. And then once it runs OP verify, it can run adapt and verify. I mean, this is a relatively simple run in 4 lines. And the problem is the following, because a different pre-signature was created beforehand, which is known by the honest signer. This pre-signature can be valid, but if this pre-signature is valid, and this signature verifies by adaptability, it must verify. However, it cannot extract because adapt will not output, like adapt will output a signature, but the oracle adapt will not output the same signature. So this problem means higher level protocols cannot rely on the extractability notion. So even if it could be instantiated, you don't have the security. And the last point we found is it cannot be realized because of local algorithms, which basically means if you have a pre-signature that is pre-verified, it can be adapted. If it's not pre-verified, it cannot be adapted, as you see here, right? This check here ensures it's adapted. However, if you look at this in the real world, the adversary can simply adapt locally and afterwards ask the extract oracle. If it does it like this, the extract oracle will return bot, which is failure. But in the real world, this extract would output a valid witness because the signature was adapted before. Again, no simulator can exist that simulates this behavior. And this means that no adapter signature scheme can be proven secure with respect to FTI. Like not only Schnorr signatures cannot, but no adapter signature scheme. I stop here for the issues we found. In addition, in total, we found 7 issues. We show that adaptability and extractability are not formalized, that it cannot be realized, and if it could be realized, you would need additional requirements from a signature scheme. And this was confusing for us. Like we thought, okay, these gaps should be like a formalization issue. Maybe it should not be hard to fix it. Maybe it was like a bunch of unfortunate typos or using stuff not in the correct way. But we found out there's like an inherent problem for adapter signature UC security. And the problem is that you have both positive properties, which is adaptability, and negative properties, which is extractability. And these both contradict each other. What do I mean by contradict each other? Well, adaptability guarantees that some signature will be valid, and extractability prohibits signatures from being valid. The problem is, in game-based settings, we consider them separately. So you have one game for extractability, one game for adaptability, and when you reason about adaptability, you don't need to take care for extractability. That's not the case in UC security. In UC security, you have both properties and they both need to hold concurrently. So at some point, the simulator needs to decide, should a signature be valid or should it be invalid? And that's a hard problem. So what we then did is we tried to build a new functionality. Or what we did is we used a different design approach, and instead of asking the adversary to provide us signatures and pre-signatures, we instantiate our functionality with local algorithms. This solves the first problem that local algorithms cannot be formalized. The problem is if you use local algorithms, you don't know if it's secure or not, right? Because the algorithm could just be insecure. So what we do then is we run these algorithms into oracles, and the oracles fix that the security guarantees actually hold. And then we can say if the fixes occur only with negligible probability, then the set of algorithms realizes our functionality. Let's look into it. So we first start with realization. So we say each oracle here locally calls our algorithms. So the pre-sign oracle calls the pre-sign algorithm, the pre-verify runs pre-verify, and so on and so forth. Then we, as in the other functionality, we store our inputs. So whenever you run pre-sign, we store, okay, rerun pre-sign. Same for pre-verify, adapt, and extract. And then we only need to fix the pre-verification and the verification algorithms. And we do it in a similar fashion to the first functionality, but in a different way such that it can be realized and is actually secure. So the first one is we look if you want to pre-verify a message pre-signature pair. We look if we already pre-verified it before or pre-signed it before. In this case, we return 1. This is again completeness. And then we look only if M is unsigned. Important here, it's not pre-signed, which would be like in the first functionality, but we only consider if it's signed or no. And if it's unsigned, to return B equals to 0. Looking ahead, this will enable us to do extractability and then return B. For the verify oracle, it's a bit more involved. So the first, we're checking if we can extract this signature that should be valid with respect to any pre-signature we pre-signed. Again, important, we consider only pre-signatures we pre-signed because extractability says the signer should be able to extract. Then we look if M sigma is already stored, which means it was either verified or signed before. Then return 1 for completeness. If this never happened, we look if the pre-signature was valid and we adapted the pre-signature. In this case, return 1. And if M is unsigned and it does not extract, we say B is 0. This looks a bit arbitrary in here, but you see we have completeness. This here ensures adaptability because whenever it's a valid pre-signature and we adapted it, it can be extracted. And in addition, we ensure extractability, which sets a bit back to 0. And you see, since we make some additional stuff in the functionality, which I didn't cover in the talk, we can have an if and an else case. So these are really exclusive cases. So either we need to ensure adaptability or we need to ensure extractability. Any questions to the functionality so far?
I guess we're all good.
Okay, good. Yeah, then looking at the time, I think I will skip this part of the talk. So in here, I wanted to talk about how to thresholdize the setting between multiple buyers and multiple sellers. And you can just look at the slides, which I guess we will upload, or look at the paper to see what's going on. Yeah, these are the papers. And I guess that's it.
You have 15 minutes if you want, unless people have.
Okay. Sorry, I thought it's until now. Then we can talk about this. Great. Okay, let's generalize the setting. So far we looked at a single buyer and a single seller. And if you have a single buyer and a single seller, it's relatively like we can solve the problem with adapter signatures because adapter signatures, as we just discussed, give us fairness between a buyer and a seller. And now what we thought about is, okay, what happens if we have multiple buyers or multiple sellers? I mean, that's a good thing to ask, no? Okay, we have a single buyer, a single seller, and this is a protocol. Now, if we have multiple sellers, the idea is, okay, let's say every buyer in this case, it's called S because it's server 1. Every buyer in here gets a share of a key, like in a threshold signature, and they compute partial pre-signatures. They send the partial pre-signatures to Bob, And Bob then can combine the partial pre-signatures into pre-signature and run the whole protocol. That's straightforward, right? So that shouldn't be a problem. However, the problem is if we look again to what adapter signatures give us. To extract the witness, the signers need to know pre-signature. However, the signers only know the partial pre-signatures, and only Bob and malicious signers maybe know the full pre-signature. So while Bob could extract, which makes no sense because Bob knows the witness, and all adversaries can extract if Bob shares the combined pre-signature with them, no honest server can extract. And that's, again, a fairness problem, but this time not between the buyers and the sellers, but amongst the buyers. So how do we fix it? And we are fixing it using a commit and open strategy. Before sending the partial pre-signatures to Bob, the signers are first exchanging commitments to their partial pre-signatures. And only when the commitments are verifying, they are sending the pre-signatures to Bob, and then Bob can combine. Okay, now Bob can combine and we committed. And how can we make sure to open? I mean, that's again a fairness issue, right? And what we are doing is we introduce a new primitive, which we call certified witness encryption. The goal we have is to find an encryption scheme which can do two things. The first thing is you can publicly encrypt shares to get a commitment. And the second goal is once you learn a signature, you can decrypt. Kind of a witness encryption where a signature is a witness. Why does this help? Well, this helps because if you go back to our picture here, when Bob learns a pre-signature and Bob eventually is paid by posting a signature, then every party in here can look at the commitments, C1, C2, C3, decrypt the commitments, also learn the pre-signatures, learn a pre-signature, and then learn the witness. And this should be doable in an efficient way. And we actually found out we can do it in an efficient way using Elgamal ciphertext. So what we're doing is we are computing a ciphertext G to the A, public key to the A and M, which is the normal Elgamal ciphertext. And we saw that if you look at a Schnorr verification, that there's also like a D-log pair going on in here. Because the Schnorr verification says verification key to the C times R is G to the S. Like that's a standard Schnorr verification. But what we can see in here, that this S is the D-log of this pair. So what we simply do is we update the Elgamal ciphertext and say, now instead of public key, or encryption key in this case, we're using now verification key of the Schnorr signature to the C times R. And then the decryption key is exactly this S value, which is SK times C plus R. So you see this ciphertext is exactly like computing the ciphertext is exactly as hard as computing an Elgamal ciphertext. However, you can encrypt whenever you know C and R, which you know before you exchange partial signatures. And you can decrypt whenever you learn a valid signature. So this witness encryption is strong enough for our application. So this kind of solves as a setting for multiple buyers. When you talk about multiple sellers, things are relatively hard and much harder than for multiple buyers. The main problem is that in the sellers talk about knowing a witness. So you kind of have a knowledge problem, not an enforceability problem, which is tough to solve. And we show that you can solve the fairness issue for sellers, but only with respect to an honest majority of sellers, and only if you have a blockchain with timing. Like without either an honest majority or the blockchain with timing, it's impossible to solve the protocol.
When you say timing, what do you mean?
Time locks. We need time locks on the blockchain. Without time locks, you can do like front-running attacks amongst sellers. And we have like two impossibility results showing that it's impossible to solve seller fairness without the time lock. And even if you have a time lock, you need an honest majority on top of it.
Okay.
I want to ask, can you tell us exactly what is the statement? What is impossible?
Okay, impossible. Yeah, so if you have, let's go to this picture maybe. Okay, imagine like Bob is now a multi-party protocol and he is talking to the buyers. And imagine you don't have a time lock. what's going on is any of these parties in here needs to send their witness share first. And if one party is sending the witness share to the other party knows both witness shares and can locally combine and adapt the pre-signature, right? Like because he knows the full witness and he knows the pre-signature. However, if this is the case, it knows the witness, and now not only the other parties here are the malicious parties, but also the second part of the sellers is a malicious party. So now these adversaries here, like the buyers and the malicious sellers, can team up together, and they will learn the witness without making a payment. Why don't they need to make a payment? Well, because if you don't have time locks, you can simply invalidate transactions on the blockchain. Right, because before an honest Bob could ever post a signature here on the blockchain, they simply invalidate it first. Does it make sense?
Okay.
Sorry?
Yeah.
Okay. And then even if you have a time lock and you don't have an honest majority of sellers, a similar problem arises, because if any honest party sends first, then the malicious parties again know the witness and can simply wait until the time lock is over. So we need to make sure that whenever any honest party is sending its share, all honest parties need to be able to recover the whole witness and to adapt the pre-signature. Yeah, and that's it. So if you want to have a look at the papers, these are the three sources, like it's the foundations of adapters, unreversible, composable adapter signatures, and the fair exchange paper. And if you're curious about other related work, we have like a paper on Eurocrypt, like me and Davide, who is in the audience, I guess, on fully adaptive two-round threshold Schnorr signatures.
Thank you. You have a few more minutes. Maybe you want to give us a preview of the fully adaptive paper?
Yeah, so what we did is for the fully adaptive paper is that the problem is similar to adapter signatures, actually, because you say you have a threshold signature scheme and the final signature must look exactly like a Schnorr signature for the same reason for adapter signatures, because the Schnorr signature may be posted on a blockchain, for example, or in a protocol that is already deployed. And if you have static security, this was kind of solved using the Frost papers. And if you have adaptive security, you only have, like before we made the paper, there were only like 3-round schemes available. And what we found out is that if you use a special technique, which we call equivocable deterministic non-derivation, you can actually boil down the existing 3-round protocols into 2 rounds. And the paper is also available on ePrint.
Any question?
So actually, I have a really bad question. What is the difference between certified witness encryption and witness encryption?
Okay, the certified witness encryption is a witness encryption, but general witness encryption is not as efficient. Certified witness encryption, we can find an efficient instantiation because the witness, like the relation for which we built the encryption, is a relation of where you have a valid signature of a special form. And the special form in here means that you have kind of a D-log relation between knowing a valid signature and knowing a public commitment. And we found for Schnorr signatures, for example, that you can use this relation to make this witness encryption, but also for example, Katzwang signatures, CL or BBS plus signatures. So in general, you could also solve this problem just using normal witness encryption. However, in this case, it would be way more inefficient.
So your definition of certified witness encryption is a witness encryption for a specific relation where the witness is a signature.
Yeah.
And the one that you have from the previous slide then.
I mean, this slide here, no? Oh. Yeah, exactly. Like, encryption kind of means you have a public key and you can get a ciphertext. Decryption means you have a signature and you can decrypt. And the interesting part is how to compute this encryption key such that you can actually decrypt with a signature.
No other questions?
There is some time I would make one. There was a talk in the office.
Go ahead.
At the very beginning, you showed the construction of adapter scheme for the D-log relation, right? My question was,
Yeah.
do you know how to do it for any NP relation? And if yes, is there any interesting application where other relations might be of interest?
So we have good question. Thank you. We have two problems in here. Like the first problem is whenever we want to make an adapter signature without changing the underlying verification equation, we need to try to use an algebraic structure in the signature scheme. And therefore, we kind of need to use like a statement witness pair, which works well with the signature, if this makes sense. The good point is that if we have a D-log relation, we can use any other hard relation and verifiable encryption. And then we simply need to exchange the decryption key for this verifiable encryption to make other relations work. Another kind of work you can try to do is use like different signature schemes. But there the problem is whenever you first have a blockchain with a signature scheme, then you try to find an adapter signature scheme. It's most of the time not the way around.
Cool. So let's thank Paul again.